Welcome to another video. So today's learning objective is to describe translations of 2D vectors, apply addition and subtraction of vectors, multiplication of vectors by scalar and diagrammatic and column representations of vectors. Use vectors to construct geometric arguments and proofs. So basically this whole lesson is all about vectors. And so let's talk a bit about what vectors are. So let's suppose you're kind of on an open field or something, right? And P marks a treasure spot, and the cross is where the treasure is. And say you're standing over here. Or in fact, let's say your friend is standing here. So your friend F is standing over here. And you need him to kind of, I don't know where you are, but you're somehow directing him, maybe through some sort of microphone or something, I don't know, some sort of communication device, maybe a walkie-talkie, I don't know. And you try to kind of direct him to the treasure. And he doesn't know where the treasure is, you have to direct him. So how would you, describe how to get to the treasure to your friend? So just to pause the video, take a few seconds to actually think about this, how you might do that. So one of the ways you might do this is, tell your friend kind of, okay, so, maybe if this up here is north, you might say something like, if this is north and this is, this is east, so you might say, you have to walk northeast for, let's say, if each of these squares is a kilometer, then 1, 2, 3, 4, 5 root 2 kilometers, for example. So you might have to walk, whatever distance that is. You might say something like that, and that's quite analogous to our bearings. If you remember that video, you'd say kind of, from north, take your compass out, and then so that you're walking in this direction for a total of a certain amount of distance. And kind of another way of thinking about this line about how you're walking from one thing to another, you might say kind of he's walking along that line as almost as a vector. So you might be saying kind of, since you're going from point F to point P, this is the vector F to P, and you would write this something like FP. And as we can kind of give it in the form of a bearing from, say, true north, or sometimes if we have coordinate axes, with X and Y, we sometimes actually give the angle from the X coordinate going, anti-clockwise. But so that doesn't come up too often in GCSE. But that's another way of giving it. So you're giving a direction and kind of the distance you walk in. Another way you might, for example, do this is if you were being a bit mean and you want your friend to walk a bit more, you might say, okay, walk 1, 2, 3, 4, 5 kilometers to the right, and then 5 kilometers up. So that's another way of kind of describing how to get from F to P. You could go like this, and then like that. And as you can see, kind of going from this to that is basically the end result is the same as going like that. So maybe I should put this end result in red. So the end result is just that, if you went along like this. Or you could, be super mean to your friend, just, annoy him for a bit, and tell him to walk backwards, and then up, and then down, or whatever, and then eventually make him get there. Or you might even, be not as mean and say something like, go right 1 kilometer, go up 1 kilometer, right, etc. But as you can see, these are all kind of different ways of telling your friend to go from one point to another. And this is what we kind of think of a vector as. It's basically, it's saying how we can get from one point on a coordinate, on a coordinate plane, usually, to another point. So if you have a coordinate plane, if I get rid of the stuff here, so if we just get rid of all these things here and pretend that kind of, say that this is the x-axis, sorry, this is the y-axis. Let me switch to my trusty black pen. Say this is the y-axis, and this is the x-axis. If we're thinking about a vector, what we tend to do is think about it from the origin to a point. So if we're looking for the point, the vector OP, the way we tend to describe it is saying kind of you go along the x-axis for however so much, and then along the y-axis for however so much. To get from O to P, which is kind of this line here, it's the same thing as if we go right along the right 5 times like this, and then up another 5 times like that. Is that 5? 1, 2, 3, 4, 5. Oh, sorry, that's 6. Is it 6 here as well? 1, 2, 3, 4, 5, 6. Yeah, it's 6. Sorry. So 6 times and 6 times. Or 6 units. We don't necessarily know what the units are. So we can say that's what OP is. To go from O to P, and we have this arrow on top to represent the fact it's a vector, and we're moving from the first thing on the left to the right, from O to P as the arrow points. It's the same as saying, go 5 right, then sorry, not 5, 6 right, and then 6 up. And kind of we've got a mathematical notation to say this. Instead of saying 6 right, we can say 6 positive in x, so plus 6 in the x direction, in x, and plus 6 in y. And the notation we have, instead of saying something like this, we'd use a column, and on the top we have kind of how many x we're going along, so 6 along in x, and on the bottom we have y, so this kind of is an x, y. So we're saying, you know, you go 6 units in the x direction, this direction here, and 6 units in the y direction, this one over here. And, you know, this vector here, if to go 1 unit along the x direction, we might call that the I vector, and if we go up 1, we call that the j vector, just as a form of notation. So we could also say something like, you know, 6i plus 6j, and these, you know, we kind of underline it to just show it's a vector basically. So that's kind of the way we represent vectors, as columns, as we can see here. If I kind of, you know, draw another out, we might, you know, so if I ask you, actually, if we go back to this, if I ask you to describe, say, this point here, let's call that, I don't know, b. If we're looking to describe the vector OB, we can say, okay, so you have to go along how many on the x-axis? 1, 2, 3, 4, 5, 6, 7, 8. 8 along the x-axis, so we put the 8 here. And then 2 up, so 8, 2. So if we look at that, we're saying go along 8 times, and then up 2. And now, interestingly, if you wanted to go from, say, B to P, let me kind of make this a bit clearer. To draw back the x-axis back in. And if we want to go, say, from B to P, how would we do that? Well, to go from B to P, the notation would be, you know, BP, with an arrow on top of it, showing that that's a vector B to P. Well, we have to go left 1, 2, and then up 1, 2, 3, 4. So that's, let me change my color pen. Okay, so we're going up 4 and left 2. And going left 2 is the same as saying, you know, going negative 2 in the x direction, in the positive x direction. So remember, this is going right is the x direction, right? So, and if that's a positive x direction, then by the same logic, going left would be a negative x direction. And same thing with the y. So if going up is the positive y, going down is the negative y. So B to P is, you go minus 2, you go left 2, and then up 4. So minus 2, 4. That's the vector B to P. And that is in general kind of how we think about vectors. And I'll walk you through some questions where, you know, we will discuss some of the, I guess, the more other properties of vectors. So the first question we have here is, if we have the vector A, you know, as this, so in text we'll have vectors represented as, so you can have vectors represented as kind of going from one point to another, as we had, for example, OP, and then a top, the arrow on top. Or we could have something like, you know, A, for example. And that bold A is kind of, you know, as we can't really do bold in handwriting, we do A with an underline underneath it, or A with like a wiggly line. It just kind of depends on preference. So if we actually go back to this, you know, going B to P, instead of saying BP, we can say this is the vector, say, C, which represents going from this to this. And kind of by that same thing, if we went, you know, if we took this line, if we copy and paste it, for example, well, let me zoom out a bit. You know, if we were to move this line along, for example, to here, this vector would also be C, because just the vector itself just represents it from going from one point to another by, you know, minus 2 and 4. You know, the vector C is not specific of where you start and where you end. Whereas, you know, BP is specific. BP is saying you start, this is the vector which starts at the point B, this is the point B, and ends up at the point P, which is here. Whereas C is just describing the vector of, is kind of the motion, I guess, of going from, going -2 and then 4. That's what C is saying. C is just telling you from whatever general point you might be, if you want to travel the vector C, you have to go -2 and then up 4. Whereas BP is telling you specifically, if you want to go from the point B to P, you have to follow the vector this. So this is kind of saying BP, to go from B to P, is you follow the vector C. So C is kind of the vector itself, whereas BP is specifying kind of the start and end point. And then it's telling you how to kind of go from that start to end point. So if we go to our question, we have the vector A as 2, 3, and the vector B is 1, 5. And if we want to add them kind of together, what we do is just say, let me go back to black pen. We write, if it's bold, we write as A with an underscore plus B with an underscore is equal to, well, A is a vector 2, 3, and B is a vector 1, 5. So let's think about this. If we're being asked to add these vectors, we're being asked to say travel 2 along and then 3 up, and then 1 along, then 5 up. So if we kind of go back to our, actually, why don't we do this over here? We're being asked to say what is that? What was it? 2 along first, and then 3 up. 2, 3. This is a vector A. And then the vector B is to go 1 along, and then 5 up. I think that's 5. And that's B. So we think about what A plus B would be, is well, we do what A does and B. So we, instead of going 2 along, and then 3 up, and then 1 along, and then 5 up, we can go 2 along, then 1 along, and then 3 up and 5 up. So we can just do this in kind of one thing. So maybe I should actually change my pen color, say to blue. So we can go 3 along, and then 8 up, to do the same as doing A, then B, in just one motion. And that's what adding the vectors really means. So we can just add kind of the top thing together, whatever's on the top. So which equals 3, and 3 plus 5 is 8. So that's our kind of resultant vector, 3, 8. And resultant vector just means kind of the end result, because when you combine them. 2A plus 3B. Okay, well this is asking us to do A twice, and then B 3 times. So we do the motion A, so we go kind of whatever A is, 2, then 1. And then we do that, 2, then 3, and then 2, then 3 again. So if we think about what 2A is, well, 2A is equal to A plus A, which is 2, 3, plus 2, 3, which is 4, 6. And as you can see from this example here, to multiply a vector by a number in front of it, which we call a scalar because it's kind of just one number, whereas vector has 2 numbers, we just kind of times each of these ones by the scalar in front of it. So by the same logic, 3b would be 3 times, so 3 into 1, 5, and we kind of do the top, times 3 by the top and 3 by the bottom, which becomes 3, 15. And now we're asked to add 2a plus 3b, which is 4, 6, plus 3, 15, which, so we can add the tops, remember? The 4 plus 3, 7, and 6 plus 15, 21. So 7, 21. See, sometimes when you're writing this quickly, what you'll do is kind of, because you have a number on the top and bottom, you might actually write a fraction. Don't make that mistake. I mean, we obviously made that mistake just by looking at it, but it's a surprisingly common mistake to make just by kind of writing that incorrectly. And now the vector C is drawn on the grid. From the point B, draw the vector 4C. Okay, well, there's a few ways to approach this, but let's think about what the vector C is. So see this, we've got this arrow here telling us the direction C goes in. So C starts from a point such as this and ends up at a point like this, which is the same thing as going 1, 2 in the positive x direction, and 1 up. So we know the vector C, don't forget this underlined thing here, is equal to 2, 1. So the vector 4C is doing C 4 times, so C plus C plus C plus C, which would be 4 times 2, 8, and 8 times 1, 4. Okay, 8, 4. So P, the vector 4C, would be going 8 in the positive x direction, and 4 up. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So 4c would be going from here up to here. And this is the vector 4c. And what you might be able to tell is that it's parallel to this kind of vector here is parallel to, oh, sorry, before I forget, don't forget to put the arrow on. It's quite important. So it's probably better to put the arrow in here than up here. So let me make that a bit clearer then. Okay, and of course this would be a straight line. I'd draw this with a ruler. And as you can see that this is parallel to this, and you'd kind of expect that, right? Because we're doing C, 1, 2, and then 1, just 4 times. So you can see how that say for example, the angle from here would be the same, and so they're parallel. So we know that if we want to consider what parallel vectors look like, if 2 vectors are parallel, they'll be multiples of each other. As we can see, C and 4C are multiples of each other, so that means they're parallel. So if we have something, a vector say D, which is equal to I don't know, say 2, 3, and the vector E, which is equal to 4, 6, we can see that they're parallel because E is equal to 2D, and that's a scalar multiple of D. So that means you do the same motion as D. Can you go the same? If you think about the direction of the vector, right? You're going in the same overall direction because you're going say 2 along and then 3 up, and then but you're doing that twice. So you're doing the same thing just for longer. So you can see how that'd be parallel. It's like, remember if we go back to our analogy of finding the treasure, say your friend was here, and you told them to say walk 2 and then 2 up, 2 along, and then 1 up. Yeah, and then saying 2 along, then 1 up. That would be the same thing as going 4 and then 2, which, as we can say, would be parallel to this first vector. So hopefully that made sense. But if vectors are scalar multiples of each other, they'll be parallel to each other. And perhaps another way of thinking of this is that there's 2 things when it comes to a vector. There's 2 things that are of interest to us. So again, going back to our initial example, if we want to tell a friend which direction to go to, we can also tell him, say the angle. The angle he has to go from, say, true north, or usually from the positive x-axis in the anti-clockwise angle. So you tell him what angle he has to go and what distance he has to travel, right? So you say, oh, go up, say, I don't know, northeast at a angle northeast and walk whatever that distance is, right? And so with a vector, there's 2 things of importance: the direction and the magnitude. So this will tell us the direction. The angle from this will tell us the direction, and this will tell us the magnitude. And if we're interested in calculating the magnitude of a vector, how might we do that? So a magnitude of a vector is the length of this line here. This line from here to here. That's the magnitude of the vector. And if we were trying to find the length of that line, well, we know the length of this line, and we know the length of this line, and that's a right angle here. So Pythagoras really helps us out here. So this is 1, 2, 3. This is 3. So 1, 2, 3. This is also 3. So this is going to be here from Pythagoras 3 squared plus 3 squared, which is 3 root 2. So to calculate the magnitude of a vector, if we're concerned with, say, the magnitude of C, we put this sign around it. So we have C and these 2 lines next to each other. That's the notation for magnitude. And then we just do the square root of this value squared plus this value squared. So 2 squared plus 1 squared, which is 4 plus 1, which is root 5. Which is just, if you remember, it just comes from Pythagoras. If you're ever confused, you think, okay, vector C is saying go 2 along and then 1 up. So overall, what's the distance or magnitude you're traveling? You're not going to go along 2 and then 1 up. You're going to walk directly. So that would just be with Pythagoras, you can work that out, 2 and 1. So this is root 5. Let's go on to another question. Okay. The vector O to A is 5A, the vector O to B is 3B, M is the midpoint of AB. Find, in terms of A and B, the vector A to B. Okay, so the vector A to B is telling us to go from A to B, right? It's saying go like this. But how do we get from A to B? Well, we don't really know what kind of this vector necessarily is. That's what we're being asked to find. So we can't do it directly. So we could do it kind of past another point. So if you want to go from A to B, we can go all the way back here, and then all the way out here. So like this, and then that. Well, to go from A to O, well, that would be the opposite direction of 5A, right? So we can say, first thing we can actually say is AB, the vector is equal to A to O plus O to B. O to B is the easy one to say. We know O to B because the direction here is given as 3B. So that's 3B. What about O to A? Well, to go from, A to O, is you'd have to go in the opposite direction of going from O to A. So to go in this direction, that would be the kind of the opposite of going from here to here. So instead of going positive 5A, you just go negative 5A. So since we've reversed the direction, we just say minus 5A. So our answer is just 3B minus 5A. And don't forget these underlines. Find in terms of AB the vector A to M. Well, if we want to go from A to M, how might we do that? Well, we know A to M is so if M is the midpoint of AB, right? That means that AM is kind of half the distance, but kind of along the same direction. So if we want to go from A to M, if we go kind of along the vector AB, but we just stop halfway, then we've kind of got to M. So there's just half of A to B. And A to B is 3B minus 3A, it's minus 5A, which, half of 3B is 3 over 2B minus 5 over 2A. Find in terms of A and B the vector O to M. Okay. We don't know, O to M is this directly, right? We don't know how to get from O to M directly. That's literally the question. To go to O to M, we can go O to A, then A to M. That's what we're being asked. O to M is the same thing as going O to A plus A to M. We know O to A, that's 5A. And we know O to M, it's a half 3B minus 5A, which is equal to 3 over 2B plus 5 over 2. And that's our answer there. And kind of perhaps a bit more generally, kind of think about these questions, an important result that we have with vectors is that, when we have vectors, for example, with, say, looking back on our initial example, you can go 3 right and then 1 up, right? With the treasure. We can think of vectors as kind of being split up into multiple parts. So going along like this and then back like this, of course you wouldn't walk that, right? If you want to go from A to M, you just walk this direct route, for example. But if we think about going past kind of A to O and then O to B, we can think, so we're going to have to go in this negative direction, right? And then we're going to have to walk back, in this positive direction again. Well, when we add them together, what we just get is the resultant vector. So instead of thinking of kind of, if we can't really think of it, vectors in terms of when vectors are combined, we shouldn't think of them as kind of walking like, in 2 separate ways. We wouldn't think about if we wanted to go from A to B, we wouldn't necessarily think, let's walk A to O and then O to B, right? We'd think, what's kind of the result if we were to walk from A to O and O to B? That's kind of what we think about as resultant vectors. So it's when we combine vectors, we always get the shortest path in that sense. So it's not something we need to worry about if we kind of going past another point to get to our destination. So even in our kind of our original example, if we have the x and y plane and we have to go from up here, for example, and we go along like this and then up like this, that's not what we're necessarily walking. We're just going this direct route. because what we're doing is we're adding this vector, which is 2, 0, and this vector is 0, 2, together into the vector 2, 2. And now we walk, along this vector, because, as the mathematician, I guess, you just see, you know exactly what direction to go to, and you know now the distance by just seeing this vector, because that's what it tells you. It tells you kind of the magnitude, because you know the magnitude if you use the square root of 2 squared plus 2 squared, which is 2 root 2. And it also tells you the direction, because you kind of know the relative lengths of x and y, right? You know that they're equal, so you'll be walking at a 45-degree angle. And perhaps if if the numbers were a bit more different, you'd use kind of something I'm going to talk about, or have I already talked about? Okay, about SOHCAHTOA. If I have talked about that already, then good, you remember it. If I haven't, it's coming up. Sorry, I forget about the order sometimes. So, we from the vector we know, say 2, 2. We know, we're going to walk in the direction, because we know kind of the relative lengths. We know from SOHCAHTOA the direction we're going to walk, and we know the magnitude. So that's what that vector is saying. Okay, another question. There's a few more questions in this, because this is vectors. The proof topic is quite difficult. This is a proof question. So O to A is 5A, O to B is 2B. A bit annoyingly in this question, they haven't actually necessarily underlined and made the bold, but C is the point on OA such that OC, the ratio of OC to CA is 4 to 1, D is the point such that AD to DB is equal to half, and the line OB is extended to the point E. Given that C, D, and E are on the straight line, find the line BE. Okay, so with a question like this, there's kind of quite a lot of information. So first thing I do is, we get that information on the diagram. So C is the point on OA, so OA, such that OC to CA is 4 to 1. So they haven't actually been too nice to us, and they actually have marked out what C is. So we mark out C, say something like this. What the question is telling us is that the ratio of O to C to A is 4 to 1. So that means this length is 4 times the length of this. So, if this is 4, this is kind of 1, I guess. And kind of, if you remember from our ratios video, that will mean that C to A is going to be 4/5 of 5A, which is just 4A, and C to A is going to be just A. So we know that from this. D is the point such that AD to DB is a half. Oh, sorry, it's 1 to 2. So again, if this is 1, this is 2. We don't necessarily know what that is yet, so we can't really label this information. We can just say something 1 to 2 maybe. And the line OB is extended, so this is a straight line, to the point E. Given that C, D, and E all lie on the same straight line, find BE. So C, D, and E all lie on the same straight line. So, oh god, that's a badly drawn straight line. Let me get my straight line tool out. It really does not want to cooperate. So it's going to have to be a freehand thing and hope for the best, I guess. Okay, that doesn't look too bad. Okay, so this is a straight line. So how do we find B to E? Okay, well, we know B to E is this length here, right? And how do we get from B to E using stuff we already know? Well, what we do know is that we can get from B to D and then D to E. That's the only other way we know. So because we're also to find the direct thing, we'll have to kind of somehow find it indirectly through another point. So since we don't know this directly, we'd have to go something like, B to D, then D to E, or maybe B to O, then O to C, then C to E, which is kind of another option. So at any rate, we need to find out where D is. We can tell that will be our first step, because any kind of indirect vector, maybe if I can call it that, has to go through D. So we can either go like this, then this, or we can go like that. But so we have to go through D basically. So it'd be quite useful to find out, say, what C to D maybe is, or even OD, for example. So what we might do, say, if we want to find kind of the location of D, we know that's kind of, so we know that lies on the line AB. So one thing we might want to start off by doing then is finding what AB is. So line A to B is, okay, well, we have to go from back this way and then this way. So we go negative 5A plus 2B, So 2b minus 5a. We know that d is such that AD and to DB is 1 to 2. So that means AD is equal to a third of AB. So if we want to go from A to D, it's just a third along the way of A to B. So if we can say a third 2b minus 5a. Okay, we know what AD is now. So, okay, so if we want B to E, we can go say maybe, like this and then that, but we don't actually know what, but the thing is we know now, say for example, what B to D might be, but we don't know what D to E is. But one thing we do know is that kind of O to E or even B to E is just going to be some multiple of B because it's along the same straight line. So that's one thing we know. So in a question like this, in all honesty, I'm not exactly sure where I need to go right now. So what you require is a bit of kind of experimentation and kind of labeling. So we know what AD is, and if we know what AD is, we know what BD is. And you might have the vague feeling that you'll have to go through D, and kind of the most direct way from getting from B to E is B to D, then D to E. So it'd be quite useful to know what B to D is. So we know A to D is a third that. And so we know, for example, D to B then is 2/3 of A to B. And we're concerned with B to D, this is poor handwriting. We know D to B is 2/3 of A to B. D to B is 2/3 of A to B. And so we know that B to D, which is the opposite direction, is minus 2/3 of A to B. And A to B is 2b minus 5a. We've got that information. Now we need to figure out what D to E is. So, now that you might struggle with this part. You think kind of what piece of information I haven't used so far. Well, we haven't used the fact that C, D, and E all lie on the same straight line. So what does that mean if they lie along the same straight line? Well, it means that kind of if we went from C to D, for example, would be parallel to D to E. So that's something we know because they lie on the same straight line. That means kind of, if you think about a line, any two sections along the line are parallel to any other section, just because they're on the same straight line. So if we find out what C to D is, that might be helpful in that sense. So let's figure out what C to D is now. Okay, well, now we have to find out what C is. Well, we know OC is just 4A. So if we want to go C to D, we have to go, gosh, what is that? C to O, O to B, and then B to D. So CD is equal to C to O plus O to B plus B to D. C to O, what's C to O? C to O is minus 4A. O to B is 2B. And B to D is minus 2/3, of 2B minus 5A. There we go. Sometimes it's worthwhile simplifying. Right now, since we don't know exactly how we need to do it, we can take a minute and not necessarily simplify. And we also know that because DE is parallel to CD, you might say something like, and so actually, sorry, if we do simplify this, and I realized that it was a bit of a silly way of finding C to D. We can just go along this and that, which is another way. So if you were thinking, oh, why are you taking the long way around? That's because I didn't spot the easy way, and that does happen sometimes. So sometimes you'll kind of kick yourself and think, oh, that was such an easier way, but sometimes you just don't spot it. So I guess you have to live with that. So if we simplify this, we get minus 4A plus 2B minus 2/3 of that. So if we simplify that, minus 4A plus 10 over 3A plus 2B minus 4 over 3B which simplifies to minus 4 plus 10 over 3. So 4 minus, if we kind of, you could use a calculator for this, or you could do this in your head. That becomes minus 2 over 3a plus, and then minus 2, 2b minus 4 over 3 is plus 2 over 3b, which becomes 2 over 3 into minus a plus b. That's what c to d is. We know c to e lies on kind of, they're the same line, they're one big line. So we know that c to e, hence, must be a multiple of minus a plus 2b, kind of 2/3 of that. It must be some sort of multiple of this, right? Because if you want to go c to d, if you want to go c to e, is, you go c to d and then kind of some multiple of that. Just it's the same line, so we kind of stretch it out, I guess, if you want to think about it like that. So we also know that another thing is that the line OB is extended, and that's how you get E. So this must have some kind of an x coordinate of 0. It's not turning out x coordinate, I guess, but it has to be something of B only, right? So if we want to go from C to E, we'd go kind of negative in C, C to O, and then O to E. So which is equal to C to O plus what was that, O to E. And we know O to E is just a multiple of B, and we know C to O is minus 4a, if we see it from here. C to O is minus 4a, and then kind of, there's not going to be any more a's involved because we're just going O to E, which is just going to be some multiple of B. So we can say plus, say, xb. We don't know what xb is. And we know it has to be some multiple of this, right? We know that minus a plus b, so it kind of has to be some multiple of this, so that means x must be 4 then. Because if we want this to be minus 4a plus xb to be some sort of multiple of minus a plus b, then x equals 4. Therefore, c to e is equal to minus 4a plus 4b. And then, if we think about what b to e then must be, c to b, so if we say ce is also equal to c to b plus b to e, we're looking for b to e. We know c to b is minus 4a plus 2b, and this is 2b plus be. Sorry, I got it on the, yes. This is on the right, left it's minus 4a plus 4b. And if we rearrange that, we get be is equal to 2b, and that's our answer. So this is a fairly challenging GCSE question, but the way to approach these kind of vector questions is, you always have to think about how can I get from one point to another, and you basically always need some sort of midpoint, or not midpoint, but kind of a point you have to go indirectly through. So a lot of the time, it actually depends what that might be, but you might want to think of the origin or something like that. And remember the fact that if they're on the same straight line, it means that kind of the vectors must be multiples of each other. That's a very crucial thing that comes up, and in fact it will come up in the next question. I know lots of questions, but vectors is a fairly tricky topic, so it's worthwhile to do a few of these questions, especially because you get different types of questions. So diagram shows a parallelogram. When you see questions like this, you have to remember your properties of these shapes, and if you remember that that this length is parallel to this side is parallel to this side, and the same thing with these, you then kind of realize that if the two things are parallel and kind of the same length, then this vector will also be 2b, and this vector will also be 2a. That's the thing we need to kind of spot from the parallelogram point. So we know O to A is 2a, O to B is 2b, as it says in the question, and D is a point on OC such that OD to DC is 2 to 1, and then E is midpoint of BC. Show that A, D, and E are on the same straight line. So we need to show that that line is straight. So how would we do that? Well, remember how we kind of use the fact that the same straight line will be multiple of each other. So we find A to D and then A to E, and we show, for example, that kind of A to D is a multiple of A to E is a multiple of A to D, and they both pass through the same point A. Then they must be kind of parallel and they pass through the same point, and the only way that can happen is if they're the same straight line. So to show, again, as a kind of repeat, to show that something is the same straight line, what you need to show is that they are parallel plus pass through the same point. So if you think about two parallel lines which pass through the same point, the only way that can happen is that it's the same line. So that's what you need to keep in mind. And what do you need to show that they're parallel? As in kind of the two vectors you find. You'll find two forms of vectors. That might be A to D and then D to E perhaps, or AE and then AD. You have to show that they're parallel by showing that they're kind of multiples of each other. That's remember what parallel means, and also that they kind of pass the same point. So what we need to do again, so if we find AE and AD, that's kind of our mission right now. So to find AD, well, we need to go kind of negative this way, so minus 2a plus whatever O to D is. So clearly we need to find O to D first. We know D is point such that OD to DC is 2 to 1. So we know that OD is equal to 2/3 of O to C. And O to C is, if we go minus 2a plus 2b, or sorry, no, 2b plus 2a. So O to B, then B to C. So OC is 2a plus 2b. And then we can say, OD is 4/3. Well, actually, there's no point in simplifying right now. And remember, we're interested in A to D. So A to D, sometimes when you zoom out a bit too much, the handwriting gets a bit annoying. So I'll zoom back in. So A to D is equal to, if we go up here, A to D is equal to, if we go A to O, and then O to D. A to O, and then O to D. A to O is negative 2a plus this thing up here. So it's probably worthwhile simplifying right now. Minus 2a plus 2/3 of 2/3a. So what is that? Minus 2a plus 4/3a plus 4/3b. So minus 2 is, what is that? Minus 6/3 plus 4/3. So that's minus 2/3a plus 4/3b. And usually when you have questions like these, when you have this kind of something like AD, which is kind of an intermediate thing we need, it simplifies nicely, or not simplifies, factorizes neatly. So this is just 2/3 into minus a plus 2b. And so we'll need to show that AE is a multiple of this. So AE, well, A to E is the same as going A to C and then C to E. And we know E is the midpoint of B to C, which is kind of, just A. So this would be, if we want to go like that, A and then A again. So if you want AE, we go A to C plus C to E. A to C is 2B, C to E is minus A. And then look at that, we have them being multiples of each other, minus A and 2B, and then same thing here. So therefore AE is a multiple of AD, and they pass through the same point, therefore parallel. And this is, when it comes to proofs, this is one of the very big things that you need to often prove, that they're on the same straight line, and that's kind of a big proof. I think that hopefully is the last question. Yeah, I know this has been a bit of a longer video, and vectors is kind of a fairly tough topic, so really important you do practice your questions, and just remember kind of, especially with the notation, it's something new, so just make sure you kind of get your underline, get your arrows. It will help you as much as the examiner, because what you might say when you have something like A, you might think, oh, is this algebra, so A is just a number, but it's in this case it's just a vector. It's actually a vector, so you need that underline to remind yourself as much as the examiner that A is a vector, and you don't kind of get that confused. So hopefully that all made sense in this video, and I'll see you guys in the next one.